current component, besides drift current density, we have a diffusion current density. And as we have mentioned earlier, this diffusion happens due to the concentration gradient. Okay, this is due to the flow of charges from a high concentration region to a low concentration region. Well, the charges are statistically moving, you see, in a lattice of a single crystal silicon or a doped silicon semiconductor. So what happens is that in one region you might have high density of charges, and they tend to move from one dense region to a lower dense region. Okay, they are moving from lower dense to higher dense, but in the lower dense region you have fewer particles by definition. So the net movement to consider is from high, let's say high concentration of charged particles to, let's say, the lower concentration. So for example, you have a high concentration of charged particles somewhere in the semiconductor, then you have fewer particles, okay, on one side. So the net movement will be from high concentrated region of charges to a lower concentration of charges. Okay, I mean, this region, high concentration region, could be more well doped. Okay, it could have more impurity, let's say atoms, and there could be more free electrons or holes in this region. And owing to the high concentration of charges, you have a net flow of charges from a high concentration, a high dense region to a low dense region. Okay, although the charges will be moving statistically from low dense to high dense regions, but these are fewer particles. Okay, so the net diffusion current that flows is from high concentration to low concentration region. So in diffusion process, the particles, they flow from a region of high concentration region to a low concentration region, and this is a statistical phenomena related to kinetic theory. Now, to explain the electron and holes in a semiconductor that are in continuous motion with an average speed which is determined by the temperature conditions, and with a direction which are randomized by the interaction with lattice atoms, because they are also being bombarded, or they get collided with the lattice structure. So the motion of these particles are statistical. Okay, they are erratic. But then that's how the movement is. Okay, depending on the temperature, how much energy they have to move around in the lattice. So statistically, we can assume that at any particular instant, approximately half of the particles in the high concentration region are moving away from that region towards the low concentration region. And we can also assume that at the same time, half of the particles in the lower concentration region are moving towards high concentration region. But by definition, the low concentration region have fewer particles than in the high concentration region. Therefore, the net result is the flow of particles from high concentration region to a low concentration region. This constitutes a diffusion current. Okay, there is no electric field. There is no voltage that is being applied to the semiconductor externally. Okay, so for example, if this is a piece of semiconductor, we are not applying any electric field. Okay, that's going to constitute whether it's an N-type or P-type. That's going to constitute for the drift current. Okay, because if you apply an electric field, what happens is that you are going to establish a force. And this force is going to, in a semiconductor, this force will be experienced by the charge carriers, holes and electrons, and they're going to experience a drift velocity due to this established electric field. We don't have any established electric field in this process. The diffusion current and drift current are two separate current components. Okay, with fortunately one component being larger than the other at one particular time and place of in a semiconductor. Okay, but again, both of these components, they constitute to the conduction of current. Okay, now let's consider this. These figures are showing the concentration gradients and as a function of distance x. And what happens is this is for, let's say, this is for an N-type material having majority of negatively charged particles, electrons. And as you are increasing the distance x, the concentration is increasing. Okay, so this is a high concentration region. Okay, and this line is separating high and low concentration regions. So what happens is that from high concentration region to low concentration region, there's an electron diffusion towards left. Okay, that's in the conventional direction of current of a flow of charge it opposes the flow of electrons. So the conventional current density is in the opposite direction of the flow of charges. Okay. Similarly, for holes, as you move in the distance, as you move on the x-axis and move to the higher values of x-axis, you have a higher concentration of holes as compared to the low value of x-axis. So you have a low concentration of holes over here. So again, there will be a hole diffusion from high concentration. There will be a net hole diffusion from a high concentration region to low concentration region, which is indicated by this arrow. The direction is the hole diffusion. And you know that the conventional current of positively charged particles, holes in this case, is in the same direction as that of the current. So the hole diffusion current density and the conventional current is in the same direction of the hole diffusion. Okay. So if you consider electron concentration, that varies as a function of distance x, as shown in figure 1.9. The diffusion of electrons from high concentration region to low concentration region produces a flow of electrons in the negative x direction. Okay. So you see you have electron diffusion in the negative x direction. Similarly, you have the flow of holes in the negative x direction from high to low concentration. It's only the conventional current directions which are opposing because of the electronic charge being different in both the n-type and p-type materials. Okay, so since electron negatively charged, the conventional current direction is in the positive x direction. So that's all. Okay, so this is a p-type semiconductor with having holes as the majority carriers responsible for current conduction. Now, analytically, the diffusion current density due to the diffusion of electrons can be written as, so you have a drift coefficient. Okay, this is electronic diffusion. This is not a drift coefficient. This is a diffusion coefficient. Electron diffusion coefficient. E is the fundamental charge. dN by dx represents the concentration gradient. Okay, now this current density is due to the concentration gradient. How much the gradient is, and depends on how much the diffusion current is at that particular region in a semiconductor. So this is a controlling factor for the drift current, the diffusion current. We are not talking of drift current. This is the electron diffusion current. Okay. Now, in this context, again, is the magnitude of the electronic charge. dN by dx is the gradient of the electron concentration, which is responsible for the diffusion current, and dN is the electron diffusion coefficient. Now, in figure 1.9b, as you've seen for a p-type, as you've seen for n-type, in part B, you have a p-type semiconductor. So we have a similar relationship, only the sign has been changed. The electronic charge is different. So the hole concentration is a function of distance again, and you have this gradient dP by dx. The diffusion of holes from the high concentration region to a low concentration region produces flow of holes in the negative x direction. Okay, it's the same thing which is going on over here. From high concentration to low concentration, holes are being diffused. So this is constituting the diffusion current. Now, conventional current is in the direction of the flow of positive charge, so you don't have any problem over here. I mean, the direction of the hole current is the same as the conventional current. So the hole diffusion current is in the same direction as that of hole diffusion, physical holes diffusing from high concentration to low concentration regions. So the diffusion current density due to the diffusion of holes can be written as such that there is a change in the electronic sign. Okay, note that. And dP again is the hole diffusion. dP becomes the hole diffusion coefficient. Okay, as we have this for the electron diffusion coefficient dN. So dP is a hole diffusion coefficient. And note the change in sign between the two diffusion current equations. This change in sign is due to the difference of sign of the electronic charge between the negatively charged electron and positively charged holes. So you know that both the holes and electrons are going to contribute towards the diffusion are going to contribute independently towards the diffusion current in any semiconductor material, and some of them Jn plus Jp is going to contribute towards the total diffusion current in a semiconductor. Okay, so this example illustrates the evaluation of a diffusion current density for a given semiconductor. So let's say this is a piece of silicon. Let's consider a piece of silicon at normal room temperature conditions, and assume the electron concentration is varying from 10 to the power 12 cubic centimeter to 10 to the power 16 cubic centimeter. That is, you see, you have a growing trend like this, right? I mean, as you're increasing, as the distance is increasing, the concentration is increasing. Okay, so the concentration of charge carriers, they increase. So you have a positive gradient. I mean, dN by dx is there is a concentration gradient which is positive, and due to this concentration gradient, you're going to have the diffusion current. Okay, and how you can evaluate this is simple. I mean, you can just take the gradient of these values, 10 to the power 16 minus 10 to the power 12, and this happens over the distance from 0 to 3 microns, right? So this is the evaluation of. You see, all you have to do is to evaluate the gradient of the concentration region in the semiconductor. So this is dN by dx, right? And this is going to constitute your diffusion current going to electrons. The diffusion coefficient for electron is given as 35 centimeters square per centimeter. So you just have to plug those values in over here with the electronic charge E. Okay, and this is going to give you the current density, which is in the order of few hundred, again, few hundred amps per centimeter squares. This density is respectable, which means that diffusion current density is on the order of few hundred amps per square centimeters. They can also be generated in a semiconductor besides drift currents. Okay, so the mobility values in the drift current equations and the diffusion coefficient values in the diffusion current equations are not independent quantities. Okay, so the mobility values in the drift current and diffusion current are also dependent quantity, right? They are related by the Einstein relation. Okay, that is, if you take the ratios of the diffusion coefficients of electrons and holes, and you have to take the ratio by their mobility. Well, this turns out to be a fixed quantity. It's about 2.6 millivolts. Okay, it can be expressed in terms of the Boltzmann constant, the temperature, and the electronic charge. So this relationship is showing that the mobility is in both the drift and diffusion coefficients is a dependent quantity. It's not an independent quantity. Okay. Now the total current density is the sum of the drift and diffusion components. So fortunately, in most cases, only one component dominates. But this, you must have to remember that the drift current is due to the applied electric field. Okay, and the drift current, VDN or VDP, doesn't matter. Let's say this is VDN, is a linear. It has a linear relationship with the applied electric field. So in case of N-type material where the charges are predominantly negative electrons, as you increase the electric field, for small electric fields, the drift velocity is increased. So there is a linear relationship between the applied electric field and the drift velocity. The drift velocity is due to the applied electric field. However, the current is different. The drift current is you have to consider the number of charges, and for that you start with the fundamental charge multiplied by the concentration of the charges N in that region, and then you have to multiply this with the with VDN. Okay, with VDN. So it's like an Ohm's law if you substitute VDN over here. So because of the application of electric field, you have the current, right? Because of the application of voltage, you have the electric current. So this is the drift velocity. But for the diffusion current, remember the diffusion current happens. Let's call this JDF diffusion current. That is due to the concentration gradient dN by dx. Okay, so that is proportional to dN by dx with a certain drift coefficient and the electronic charge, right? So these two components, the diffusion current component and the drift component, are basically are two current components in a semiconductor that are contributing towards the conduction of current. Okay, but fortunately in most cases only one component dominates the current at any one time in a given region of semiconductor. Okay, that's all.